Now that we've talked about local maximums and minimums in the last video, can we use those to find the absolute highest and lowest points for a function on a given region? We were able to do that in Calc 1 by using something we had that we called the extreme value theorem. That said if we had a continuous function on a closed interval, so some f sub x on something like AB, where it's closed interval, we necessarily have both a maximum and a minimum. We even were able to tell that the maximum or minimum must either be at a critical point on the inside, so a critical point on the open interval a to b, or it could be at one of the endpoints a or b. For a function of two variables, it does get a little bit more complicated because we're not just going to be dealing with some interval. We're not going to be dealing with a closed interval from a to b. And we're going to be dealing with some weird shape or possibly a weird shape in the plane. So we're going to have to make sure that our whatever region we're trying to find the maximum or minimum over, it has certain properties to make sure things do work the way we want them to. So we're going to generalize this idea of having a closed interval and use that to actually get some idea of how we might be able to find maximums or minimums of functions of two variables. So we're going to start with the idea of being closed. We're going to say a region is closed, a region in the plane, though we can actually, this definition that we're going to be using here can actually extend to regions in three-dimensional space if we prefer. But we're going to say that a region is closed if it contains its boundary. If it contains all points in its boundary. So let's kind of just draw a picture of something like this. If we're working in the plane, we have some blob here. It's our region. All the points along this curve that I drew is the boundary. And we're going to say this can only be a closed region if every single point on that boundary has to be included in that set. If we leave even one point out, it's no longer going to be a closed function, or a closed region. Technically, to say whether a point is on the boundary or not, say a point over here, if we were to draw a disk around that, no matter how big of a disk we draw, it's going to have points that are inside or points that are outside. That's not going to be true if I say a point even a little bit close here. I can always find a small enough radius that doesn't go inside. Or if I draw a point inside, I can always find a small enough radius that doesn't go outside. But a point on the boundary cannot have that be true. Now that is more the formal definition of what boundary means, and since we're not going to get into any of the weirder kind of possible subsets of the plane, we're not going to really care too much about that. Boundary just basically means what you think it means. It's any point on the edge of it. So just kind of some examples of things that can happen. So a closed set might be something like the closed circle, say the unit circle, or say a box. If you look at the box from 0, 1 along the x-axis and 0, 1 along the y-axis, as long as we contain those points along the boundary, we're fine. If we don't contain that boundary, we usually, when we don't contain the boundary, that's when we're using these dashed lines. So if say we take the unit circle, but we include the inside of it, but not any points along the circle itself, we actually call that an open set. And we can kind of do the same thing with the box as well, though a little hard to draw along the axes there. That's also an open set. Now, if it contains some points on its boundary and not all of them, we don't say it's either one of them. So something like, what if we contain the bottom half of the circle, but not the top half? So we contain all the points inside here and the points along the bottom semicircle. This is not open because it does contain points on its boundary, but it's not closed because it doesn't contain all of them. So technically here, we're looking at all the points inside of our sets. In fact, even if we contain almost all the points, but we're missing one point, we're missing that top point there. This contains points on its boundary, so it's not open, but it doesn't contain every single one of the points on the boundary. It's missing a single point here, so this set is not closed. So, kind of getting a little technical here, but it is important that we do have a closed set in order for this to work nicely. But it actually turns out closed is not enough. So, in the real line, we have closed intervals like AB. Those are closed intervals. But technically, we also include an interval like a to infinity. This is a closed interval, even though we don't put a bracket here, but because it contains all points along its boundary. So here, a is its boundary. It doesn't have a boundary on the infinity side because it never ends. In a similar way, negative infinity to b, as long as we include that b, is also a closed interval. But the extreme value theorem for functions of one variable specifically requires us to be dealing with the function of in an interval of the form a to b. These two don't work. In fact, it's not true if we were to try to include those. And the point here is that we need our intervals to not go off to infinity. And we're going to need that for sets in the plane as well. So we're going to say a set is bounded if it doesn't go off to infinity. And formally what that'll mean is the set can fit inside some disk. So if I were to draw a picture here, I can have my blob. Oh, some weird blob there. But the point is that I can pick some center and some radius so that that set is completely inside. Maybe I'll make the center over here so it looks a little bit better. There is some disk, some circle I can draw around the entire thing. If this blob went off to infinity somehow, even if it's only goes off to infinity in a very narrow region like that, there's no way I can draw a circle around the entire thing. That's all we're really saying. Is it doesn't go off to infinity if we can draw a circle around it, basically. And it doesn't matter how big of a circle that is. Whatever, if that disk has a really big radius, that's still fine. It just needs to not be infinite. It needs to be a finite radius. So that's all we really need to state our theorem. So our extreme value theorem for functions of two variables, we have to have a continuous function of two variables on a closed bounded set. We need both those conditions to be there. There's actually a term for a more general term for those called a compact set, but you won't run into that kind of term unless you take a more advanced course on calculus or topology. So don't worry about that. But the point here is that as long as we have those two conditions of closed and bounded, then and our function is continuous, then f is guaranteed to have an absolute maximum value in the set and an absolute minimum value in the set. There's some points in that set that give us the biggest value of f possible, and a point where it gives it the absolute smallest value of the point possible. We can find those points by either looking at critical points on the interior of the set, or because they could happen on the boundary, those may not be critical points. So we might have to do something a little bit more. But we can actually summarize all that in a this theorem here is pretty much going to just be our outline for how we're going to approach these kind of problems. We're going to look at values of f at the critical points inside the region. So we're going to start by looking at critical points, and we can even exclude the points that are not in the region, because we will have to define what that region is for any problem that we're working on. Then we're also going to have to look at any possible extreme values on the boundary, and that's going to be probably the trickiest part of this, at least at first. So it will. For now, we're only going to be able to look at some of the easier boundaries, things that are made up of lines or circles. Maybe our region looks like some sort of triangle or rectangle, something like that. That's all we really can work with right now. If our boundary is some more complicated curve, we're going to need a little bit more, and that's what we're going to actually address in section 14.8. In fact, we'll even go a little bit further and be able to talk about boundaries in three-dimensional space. So three-dimensional blobs instead of two-dimensional blobs. And we'll be able to maximize things over those boundaries. And note here that we don't really have to use the second derivative test to test whether or not we have local maximums or minimums for the critical points inside the region, because all we're really going to do is compare the values of the functions at all those points. So let's actually just go ahead and work some examples. So here we have a function of two variables, x squared plus y squared minus 2x. Our region, D, is a triangle. It's a closed triangular region with vertices 2, 0, 0, 2, and 0, negative 2. And before we even go ahead and get started on this, let's actually draw this thing. Now, I'm not sure how much you've played around with GeoGebra yet, but it does have some very nice geometry features. I'm going to go ahead and plot the vertices of my triangle. We have the point 2, 0, 0, 2, and 0, negative 2. So we have these 3 points in the plane. We can actually go ahead and select the polygon tool up here and actually click on these points, and it will go ahead and draw in the triangle that has those as its vertices. You can actually do that with any polygon you want. In fact, if you want to do any sort of geometrical constructions, play around with some of these tools. They're very, very nifty things. But the point here is we've drawn our region in the plane. We're going to be looking at a function, f of xy is equal to x squared plus y squared minus 2x. So we have this paraboloid, but we're really only concerned with the part that is contained in that triangle. So only the stuff that's in there. And GeoGebra doesn't really make it easy to only show that part, though it is possible to do that with what we call an if statement. But to actually do that, I'm going to have to turn my region into some sort of condition on x and y. In fact, the condition here is that x is going to be between 0, so we don't have any 0 values, and then I have to somehow give a condition for this boundary in terms of y. It turns out that we need that x is less than 2 minus the absolute value of y. And we want GeoGebra to plot all points on the surface using the function f of x, y that we already have defined here on that condition. And let's zoom in here so we can see a little bit better. So it's showing us only the part that's in that region, though GeoGebra can have an issue with corners sometimes. So it's actually not really showing us everything. It's I don't know. It's a useful idea to use an if statement, but it doesn't always work as well as you might want it to. But at least we kind of get an idea of what's going on here. You can actually see what's happening. So you can already kind of tell that we're going to have a minimum inside of the region. The maximum is probably going to be at one of these endpoints, or probably both of them. But let's actually go ahead and do the math and show that those are actually true. So we need to do multiple things here. First, we're going to remember our breakdown here. We're going to look at critical points inside, and then we're going to look at the boundary. So let's start with the inside, because that's actually going to be maybe the easier part of this. So let's just say inside. This is the kind of stuff that we were doing in the last video. We're taking this function, we're looking for its critical points. We're not going to have to use the second derivative test here. So I'm going to look at what is f sub x, the derivative of this with respect to x. Hopefully by this point you can tell that that's going to be 2x and minus 2, the y squared goes away. And that's eventually going to have to equal 0. If we look at f sub y, derivative of this, well, the x1s go away, we have a 2y, and that's going to have to equal 0. And it turns out we only have one possibility here. So this says that y equals 0, and this one says that x equals 1. So that's our singular critical point. Which, if you remember our drawing, is probably going to be the absolute minimum, but again, we are going to prove that. But that's our first step, looking for those critical points. Now let's look at the boundary. I'm just going to abbreviate as BD. Now, how are we going to deal with the boundary? The boundary here being 3 different line segments. How are we going to deal with those? Well, we're just going to treat those as 3 different parts of a boundary. If we have 3 lines, we're going to think about those 3 lines separately. So let's say the line, let's actually start with the easier one, the line from 0 to 0, negative 2. That part of the boundary is this part along the y-axis. So that's actually a very nice equation for that line, is that x equals 0. We're essentially saying here that x equals 0 with the y values going between negative 2 and 2. If we go ahead and plug in this formula for x, just plug that directly into f of xy, we're looking at f of 0y is equal to just y squared, and we can actually just treat this as a function of y. And we're just asking how do we maximize or minimize this function along that part of the boundary? Now this is just a function of one variable. We can find its critical points like we did in Calc 1. The derivative of this is 2y. That equals 0 when y equals 0. And so what does that mean? Well, that means we get kind of a critical point on the boundary of 0, 0. Remember, the x is equals 0 there. So we get a point 0, 0 that is not a critical point of the original function, but it's a critical point of this restriction to the boundary. So it's something that we're going to have to include in our calculations. We're going to have to look at that point and see what happens. And you can kind of already tell what that point represents. If we just look at that cross section along the y-axis, it's the lowest point of there. We also, because we're basically looking for the absolute maximums and minimums of this function y squared on this interval from -2 to 2, we're also going to have to include those endpoints as well, because those are possible places that could maximize or minimize the function on that region, on that interval. So we're also going to include the points 0, -2, and 0, 2. That's one part of our boundary. Now let's look at another part. Let's look from 2, 0 to 0, 2. So that is this one that GeoGebra has labeled C. It's that line. And we're wanting to somehow turn this similar to what we did here, where we turned it into a function of one variable. Well, we can do that by actually finding a formula for the line. So that line is actually y equals 2 minus x. With our x values, x is going between 0 and 2. Hopefully you can kind of figure out how that makes sense. But I just have a line, I find an equation for it, and then I find what the extreme values of my x can be. I can go ahead and plug those into my function, just replacing y with 2 minus x. That's going to be a new function of x. I'm not going to come up with a new name for it. If I go ahead and plug those into it, we have x squared plus 2 minus x squared minus 2x, which we can actually expand out and get 2x squared minus 6x plus 4. If we differentiate this thing, this becomes a 4x minus 6, and that equals 0 when x is equal to 3 halves. And of course, that means we are going to then go ahead and put 3 halves, find the y value using our formula for our line, which is 1 half. And then we also look at our endpoints. Endpoints here being 2, 0 and 0, 2. Because those are just our x values. If we plug in 0, we get 0, 2. If we plug in 2, we get 2, 0. Again, just using our line. But we're on these line segments, we're turning our function into a function of a single variable and using Calc 1 techniques. From 2, 0 to 0, -2. This time our line is actually x minus 2 with the same limits on our x's. If we go ahead and plug those in this time, well, keep in mind we are just plugging it into y squared in here. So the square doesn't even care that we turn 2 minus x into x minus 2 because those are negatives of each other. In fact, I mean, that's really what it is. This line B is just negative to line C. But the square here gets rid of that, and so we actually get the same result. We get this 2x squared minus 6x plus 4. If we maximize that, we don't even have to repeat the work that we did before. We're going to get that x equals 3 halves. So that gives the point 3 halves, and Not the exact same point that we have here, because we're going to take that 3 halves and plug it into y equals x minus 2 this time. So the y value does change. We get a negative 1 half, and then we get our endpoints again of 2, 0, and 0, negative 2. So we're kind of repeating a few things here. We got repeats of our endpoints, but I mean that's basically what we have to do. We have to keep in mind all these different possible points. But now, how many points do we have? We have 1 point here. We have a point here. We have, well, I guess we have these 3 critical points of these 3 functions. But then we also have the 3 vertices of our triangle. Let's go ahead and just put those into a chart. In fact, I'm just going to put x and y, and then the value of the function at that point. So kind of starting with our interior critical point, we have our critical points along those boundary regions. We have the 0, 0 from the y-axis. We have the 3 halves, 1 half from our C line, the one in the first quadrant. We have a 3 halves, negative 1 half from the line in the fourth quadrant, and then we have our vertices of our triangle. Lots of different points. We're going to take all those, plug them back into our formula. Remember that our formula is x squared plus y squared minus 2x. Probably the easiest one is the 0, 0. Everything has an x in it, x or a y in it, so we get 0 overall. If we put in 1 and 0, we actually get a negative 1. If we plug in 3 halves, 1 half, we get a negative 1 half. Actually, the exact same thing for the 3 halves, negative 1 half. For 2, 0, we get a 0. For 0, 2, we get a 4. And for 0, negative 2, we also get a 4. I'll leave it to you to actually calculate those for yourself to verify what I've done here. But once we have all these possible points, we see which one gives us the biggest value of f. That's actually these two. These both give us an absolute maximum. The maximum doesn't have to work at a single point. It's just where are the highest points on our surface. If that happens at more than 1 point, those are all absolute maximums. Which one's the lowest point? That would be the negative 1. So this is our absolute minimum. And of course, though, all that agrees with what we expected. If we go back to our graph, we said that the interior point, the point at 1, 0, be 1, 0. We actually calculated the value to be negative 1. So that is the point at the bottom here. That is our absolute minimum. And then the points at 0, 2, 4 and 0, negative 2, 4. Those are both technically on our surface if GeoGebra actually showed it going all the way to those corners. In fact, if we go ahead and plot it still doesn't even show it because it's not showing us that high up. Let's zoom out a little bit. So those are definitely points that are on the boundary of our region and are on the surface, and they are the highest points on that surface that are inside that triangle. Okay. So hopefully all that makes sense. But let's look at another problem. On this problem, on problem 36, our region, it might be a little hard to see exactly what's going on there. The main important thing here is the x squared plus y squared is less than or equal to 3. That is a circle. We're looking at the interior of a disk, but we do actually have these two other conditions that x is going to have to be positive or non-negative, and y is going to have to be non-negative. So let's actually plot that region to see what's really going on. So we're going to go ahead and start with our circle. Um, I don't really want that to be here. I want it to be over here. Let's actually make it an inequality. If we go ahead and say x squared plus y squared is less than 3, there we go. Now it's showing us the disk in here. And it's actually showing the disk over here. Yeah, let's go ahead and leave that. But notice that we are only looking at places where x and y are non-negative. We're only looking at this part up here. So I don't really know an easy way for it to kind of just cut that part out. But if we say that yeah, I don't know. GeoGebra doesn't really give me an easy tool to actually just show you that quarter circle. But we are just kind of taking this quarter circle that's in the positive in the first quadrant, and then we're looking at the function f of x y is x times y squared. We get this surface here. If we only want to look at the part that's in the region that we care about, we can go ahead and try another if statement. It's going to be kind of a fun if statement here. We need x to be positive, y to be positive, and this condition x squared plus y squared to be less than 3. And then when we do that, we go ahead and tell it to give us all the f of x, y values that satisfy that condition. So we get this region over here. Again, it has a little bit of an issue with the corners. That's unfortunate. But we kind of get this shape here. That is only in that first quadrant quarter circle using that function. But we're going to go through all those same steps to actually show it, to find those points. So we're going to look at the inside. We're going to look for critical points. So that's not too hard here. The derivative with respect to x is y squared. Derivative with respect to y is 2xy. If those equal 0, well, our first one gives us that y equals 0. That's not too hard to see. But if y equals 0, then 2xy is 0 for any x. So there's no restriction on x. That's kind of an interesting condition. So we actually do not have, well, we actually have critical points all along the x-axis. Every point on the x-axis is a critical point of this function. And the x-axis is part of our boundary, or our boundary is part of the x-axis. So let's kind of just leave this here. We'll just note that this does give us a lot of critical points, and we're going to have to include those in the long run. But just this is a kind of a situation we haven't run into before, where we have a whole bunch of critical points that are in an entire line. But it is very important to note that we didn't get any critical points on the inside of our region. We only ended up with critical points on the boundary, which can happen. So let's just move on to the boundary and just go from there. Again, our boundary actually has 3 pieces. We have the piece along the x-axis, we have a piece along the y-axis, and then we have this quarter circle. Again, similar to the last problem, we're going to have to split that up into 3 pieces. We're going to have to consider all those differently. So first things first, we got the one along the x-axis, which the equation for that is y equals 0. But f of x0, if we plug in 0 for y, we just end up multiplying x by 0 and we get 0. If we look along the y-axis, then the other part of our boundary, this time x equals 0, and for the exact same kind of reason, no matter what y value we pick, we always get 0. So technically here, every point is a maximum and a minimum along that boundary, and so we're going to have to include all the points along both of these parts of the boundary. You can kind of see already that along these boundaries, we always are along always on the xy plane. We always have a height of 0 along those points. So technically here we have a lot of critical points, a lot of points to include. Though most of them we're just going to end up getting the same kind of result. So our last part, this is our circle. This is the interesting part, the quarter circle. So this is given by our equation x squared plus y squared equals 3. In order we need to turn our function on the circle into a function as a single variable, so we can use our calc 1 techniques. One way that we can do that, and this isn't necessarily the only way to approach this problem, but one easy way to do it is to start by looking at a parameterization of the circle. Or actually, maybe we can even take advantage of what we know about our curve here, or our surface. Our function is x times y squared. If we were to solve for y squared, we can actually make use of that. Y squared is equal to 3 minus x squared. This actually gets around having to work with the parameterization. So if we were to, technically, when we solve, we could say that y equals the square root of 3 minus x squared. We don't have to put a plus minus here because we know that we're only looking at y's that are non-negative. But technically here we are, say, making a function g of x, which is, in a technical sense, f of x comma this expression. But what we're really doing is we're replacing the y squared in there with 3 minus x squared. So we're taking x times 3 minus x squared. Or in other words, 3x minus x cubed. That's probably the easiest way to tackle this. And it's probably what they intended, even though that's not necessarily obvious to do it that way. But the point here is we have a function of a single variable. Technically here, the x values are going from 0 to, I guess, technically square root of 3. Those are the boundaries on this. If we look at the derivative of this function, get 3 minus 3x squared. And if we want that to equal 0, that means, let's just go ahead and move the 3x squared to the other side. Divide by 3. And we get x is plus or minus 1. Of course, here, x is going to have to be a non-negative number, so we actually get rid of the negative 1 solution. So we have x is 1. And in that case, when we plug it in here, say 3 minus 1 gives us a 2. So you end up with a square root of 2. But we also do need to include those endpoints. So the endpoints, first one where x equals 0. If x equals 0, then y is equal to square root of 3. And then I mentioned before that the other one was square root of 3, but basically that's just because that's where y equals 0. We plug square root of 3 in here, we get 3 minus 3, and we get 0 overall. But basically those correspond to this point here and that point there. Or wait, yeah. Those are the two endpoints of our quarter circle. We need both those endpoints. Though technically those will also even be included in the x-axis and y-axis that we have along the other parts of the boundary. So really, when we make our chart, we're not even going to really have to include those. our chart, and I'm just going to put xy here and f of xy here. We're going to have multiple parts. We're going to have the x-axis, we're going to have the y-axis, and then we're going to have this point, what was it? 1 square root 2. No matter what point on the x-axis we put in, or what point on the y-axis we put in, we already saw that both of those always give a 0. So that's why I'm including them here as just entire groups that all always give us the same value of 0. Obviously, the 1 square root 2 is going to be the more interesting one. F of 1 square root 2, we're going to have to plug that into our formula here. We have 1 times the square of square root 2, so we end up getting 2. So obviously here, our biggest value is 2. This is going to be our absolute maximum. And then our lowest values are all these zeros. These are our absolute minimums. There are a lot of minimum points, though they all have the same minimum value. The value is kind of the more important thing. The value of 0 is the important thing. But it is kind of nifty to see that we have a whole bunch of points where it assumes that minimum. Of course, we can kind of already see why that's true. So we have our maximum point up here. That's going to actually be at our point. It was 1 square root 2 comma 2. That is the point up there at the top, just how we predicted. And then every point along the x-axis, this one's the x-axis, and the y-axis, those all give us a point 0. Yeah, it's kind of an interesting situation here. We didn't really run into that in other situations. But the point here is I wanted you to see a lot of different possibilities and how we might approach those possibilities. Sometimes we just end up with an entire line of critical points. And we just have to know, we just deal with that whole line and see what happens. It's just kind of what we have to do. Of course, if we were to be doing anything with the second derivative test, those would actually break that test because we will get a d equals 0 in all those cases. But when we're doing these absolute maximum and minimum problems, we don't have to worry about that possible test. We can just kind of see, well, what is the value of the function on that line? And it works itself out. Obviously, the issue is being able to find all these points, whether or not our equations are easily solvable, whether it's easy to find the points where f's of x and f's of y both equal 0 at the same time. That's not necessarily an easy thing to do. But I'm not going to give you anything where it gets too bad. And if it does get too bad in a more real world situation, that's probably when you go ahead and use computers. The book even has some problems that ask you to use computers to do them. I'm not going to assume that you guys know how to necessarily do those, but if you do know how to use a computer to do that kind of stuff, feel free to try your hand at some of them. They're kind of interesting. But I'm going to go ahead and leave that here. This has been actually 2 long videos, though we've only really worked 5 examples. It just kind of shows you how long these problems can get. So I don't really want to go any more on about these kind of things. I'll see you guys in the next section, the last section of this chapter, and the last section before our first exam, where we'll actually deal with having more complicated boundaries. Another way we might deal with this quarter circle, you could say, or something even more crazy than the unit circle, or not the unit circle. This is a circle of radius square root 3, not a unit circle. But see you guys in that next video.